Okay, hello everybody. Thank you for coming. So today I'm going to be talking about some joint work with Sam Lindley and Philip Wadler. So my talk today is really about communication-centric programming languages. Communication-centric programming languages put communication and concurrency really at the very heart of their design. These programming languages all have many common features. So for example, we've got lightweight threads, often scheduled by the runtime system. We have coordination, which is done through message passing as opposed to shared memory. And we have inbuilt primitives for sending and receiving messages and spawning new processes. Now, if we zoom in slightly, we can see two particular models that are used within these languages. So languages such as Go have anonymous processes which communicate either using rendezvous points or buffers. Asynchronous channels. Now, languages such as Erlang are built, they're inspired by the actor model of communication. So this was described by Hewitt, and the actor model is basically addressable processes, each with an incoming message queue, which can spawn a new set of actors, send a finite set of messages to other actors, and change how they behave upon receiving the next message. Now, there's a surprising amount of confusion between these two models. So a quick Google search will show many different questions asking, what are the differences between the actor model and channels and CSP? Are they similar? And this confusion isn't just restricted to Stack Overflow. So there's evidence of the terms being used imprecisely in academia too. Now, another reason to actually care about these two models and look into them in a bit more depth is to give a formal grounding for some existing frameworks. So in particular, I've been particularly inspired by these two particular frameworks. So ACCA, which is the main actor framework for Scala, there's ongoing work on ACCA typed. So whereas actor mailboxes are generally untyped, ACCA typed aims to make mailboxes typed in order to increase guarantees on program safety. The proto-actor framework emulates actors in languages where they're not native, such as Go and .NET, and it would be quite interesting to formally describe the implementation strategies here. So our approach is to define two really tiny minimal calculi and define translations between them. We describe a calculus Lambda CH, which describes typed asynchronous channels, and Lambda ACT, which describes type parameterized actors. We then do translations between them, showing how one can emulate the other, and in particular, the interesting part is the issues which arise during the translations. So the contributions to this paper are as follows. We describe these two minimal calculi, Lambda CH and Lambda ACT, along with associated meta theory. We then describe translations between the two. So these translations are type and semantics preserving. Now, the really interesting thing here is that the first translation from actors into channels it's rather straightforward, but it is in fact a global translation. The latter, from channels into actors, is much more involved, requiring more base language features. However, it is in fact a local translation. We then describe two extensions to this work. First is actor synchronization, which makes the latter translation much easier. And the second is Erlang-style selective receive. So while this is baked into Erlang, we show that there's really nothing magical going on. So without further ado, I'll quickly describe the calculus. So I'm aiming to keep this rather high level. So Lambda CH is the simply typed lambda calculus described in a style of fine-grained call by value. All that means is that we split values and computations into two different categories. As well as that, we see some extra additions. We add an extra type, chanref, which is parameterized over a particular type. So this is a reference to a channel. We also describe 4 different communication and concurrency primitives. In order to go over these, it's probably best to actually have a look at the typing rules. So forks off an anonymous process. So we've got some term of the unit type. We fork it off, and we just get the unit type back. So there's no interacting with this process directly. It is completely anonymous. New CH gets us back a new channel, and give allows us to send a value along a channel if the types match. So, for example, we can send an integer along an integer channel, but not an integer along a string channel. Take receives, say we've got a channel of type, channel ref of type A, we can then get an A out of it. So an integer channel, we get an integer back. Now, instead of bombarding you with reduction semantics and runtime syntax, I'm going to go through this by example. So here is a simple program which creates two channels, forks off a new process, sends 5 along the argument channel. The fork process will then receive from the argument channel, double the value, and send it back along the result channel. So this is our starting term. And when we evaluate the new CH, what we get is a new scope and a new channel. And we see that we've got this new runtime name A, which we then substitute in for argch. We do the same for res.ch, getting a second scope B and a second channel, substitute that through, and then we fork off this new process. So on the left-hand side, we've now got return unit, and we've also got this new process on the right-hand side. Now what we can do is we can interact with these channels. So we can give 5 to the A channel. It can be received by the other process, substituted through, doubled, and substituted through again, sent along the result channel, and then we've got a program, where both processes have returned values. Okay, so now I'm going to talk about Lambda Act. So here, it's much of the same. So we base ourselves again on the simply typed Lambda calculus in fine-grained call-by-value style. The differences here are, firstly, a new set of communication and concurrency primitives, which I'll get to in a second. Now we've got a typed actor reference. So this is like what I showed you earlier with actor typed. So actor ref parameterized over a particular type. But you'll also notice that the function arrow is annotated with some type C. So this type C, this function arrow can be read as a function from A to B where we can receive messages of type C. Now, we're considering type parameterized actors here. Whereas before we could just get the type of take from the type of the channel, our type for receive is now rather context dependent, since it's dependent on the type of the mailbox. So we now have a new term typing judgment here. So you can read this judgment as, under environment gamma, and with the ability to receive messages of type B, term M has type A. So let's have a look again at the typing rules for the core communication and concurrency constructs. Spawn says that if we have got some term M, returning unit, which is typable with a mailbox type of A, then spawning it off, we'll get an actor reference parameterized over A. Self will get us our own process ID back. Send is very similar to give, so we can send to an actor if the type matches. And finally, receive retrieves a message from the mailbox, and you'll notice here that there's no argument to this, it's a nullary function. So having another look at another example, what we've got is a process which, an actor process which does much the same. So it gets its own process ID, spawns off a new actor, sends 5 to that actor, the other actor doubles the result and sends it back, and we receive. Now the first thing you'll notice here is this process, whereas it was floating around on its own before, has to actually be in an initial configuration. So we're in a scope, and we've got our own mailbox, and this is evaluating in the context of a named process A. So the first thing we do is we get our own process ID back, so we return A. We substitute that through, so where we had parent PID before, we've now got A. Now we spawn off the next actor, which is created over here. We get ourselves a new scope, return the newly created process ID, send 5 to that actor, which receives it from its mailbox, substitutes it through, doubles it, and sends it back. Now, notice that there's no intermediate computation at all, no intermediate entity. This communication is all point-to-point. Now the actor on the left can just receive from its mailbox, and we are at a point where everything is value. So let's have a look at some of the translations. So the first translation, as I said earlier, is somewhat more straightforward. The main idea is to have an actor process and to emulate the actor functionality by having a distinguished channel which represents the mailbox. In essence, it's really pinned to this process. Now, we thread the mailbox channel through the translation on terms. So the translation on types tells us, well, whereas before we had an actor reference, now we've got a channel reference. So we're addressing this distinguished channel directly. Our translation on function arrows, where function arrows from type A to type B, where we can receive messages of type C, takes an extra parameter here, which is a channel reference, and this is where the kind of global translation comes in. The translation on values, correspondingly, our translation on Lambda abstractions takes this extra parameter here, this extra Lambda abstraction, and translates the function body with respect to this distinguished mailbox. Now, the translation on communication and concurrency primitives is as follows. The idea is that the translation on primitives takes this CH parameter at the meta level and uses it to emulate context-dependent operations. So what spawn does is it creates a new mailbox channel, forks off a new process, and this is translated with respect to this newly created mailbox. And finally, we return the channel reference. Self just simply returns the channel reference, and send translates very straightforwardly to give. Finally, what we do with receive, in order to emulate receiving from the mailbox, is simply to take from this distinguished channel. Now, the translation in the other direction is somewhat less straightforward. The reason for this is we're going from a more restrictive model, a model with more restrictive patterns of communication, into a much less restrictive model. So, in fact, this translation requires some extra base language features, in particular, sum types, product types, recursive types, and fixed points. Now, the key idea of the translation, in particular in order to preserve channel mobility, is to emulate each channel using an actor. Now, a problem which arises when we talk about type parameterized actors is this notion of type pollution. Now, this means that when naively done, a typed actor must have a rather coarse-grained type. In fact, its reference type must contain all different messages it might receive in the system. So to give you an example, here is a simple three-layered system where we've got a client which sends a joining request to a chat server, which forwards this to a particular chat room. The chat room then responds, sends the response back to the client. Now you'll see here that wherever we use this actor reference with join request or join response, we need to send a message with the correct sum injection. Now this really becomes problematic in the translation in this direction. The main point is, what type do we give the mailboxes of actors which are emulating threads? The key technical thing that we do, the technical workaround that we do to do this paper without synchronization, is to require that all channels in the same system have the same type before we do the translation. We also show a coalescing transformation which cannot safely assign general enough types to all of the channels. With this, what we can do is we can rewrite the Lambda CH judgment as this particular one here, which says that under environment gamma, where all channels carry values of type B, M has got type A. So the actual translation on terms, I've hidden a lot of it away. So take my word for it. Body here is a meta-level definition which encodes an event loop in the core language. The translation on types is done with respect to a particular channel type C, so keep in mind we're assuming that all channels have this type. And then we translate a channel reference as an actor reference which can take either a request to queue a value or a request to dequeue a value. And we also use this type to annotate function arrows. Forking spawns an actor, throwing away the process ID. We actually get a bit more information than we actually need for that translation. Give sends the left injection of a value. Take sends the right injection of a value with our own process ID. And finally, new CH spawns a new actor emulating the event loop. Okay, so just to wrap up. There are two extensions that I really wanted to talk about today, and unfortunately broke my heart a bit, had to cut them from the talk. But synchronization actually allows us to do synchronous calls within actors. So this is communication which doesn't happen via the mailbox. And this really cleans up the translation from channels to actors, since we don't have to ensure that all actors have the same all channels have the same type before doing the translation. The second is selective receive. So Erlang has a mechanism for allowing us to go and process messages out of order. And this has got quite a complex reduction rule. The really quite interesting thing here is that there's really nothing magical about it. We can emulate it with plain Lambda act. And the key differences that we found in terms of comparing these calculi and the type setting is that, firstly, process addressability. So actors are addressable directly, whereas processes in the channel case are anonymous. And this has ramifications for things like supervision trees, for example, giving code a name. We also found that communication over channels is far more liberal than the mailboxes, and this really shows up in the translation. Again, the granularity of typing of mailboxes is really quite coarse. We end up having rather large variant types to describe actor mailbox types. And the final concerns message ordering. So there's always a temporal order on messages in a mailbox, less so on channels. So to conclude, channel and actor-based languages are quite widely used, but there is some confusion that remains. What we've done in this work is we've defined two tiny models for languages based on channels, languages based on actors, and we've done translations between them. This makes folklore explicit, gives a very crisp characterization of the problem of type pollution, and we show that these languages can be modularly extended. Ongoing work at the moment is using the lessons learned in the design of a full-fledged distributed language with session types being a type system for communication protocols. Okay, thank you very much.
Hi, thanks. So I have a technical question about why your send primitives or your give requires values as arguments, because that seems to...
Right, okay. So great question, brilliant question. So it really helps with us reasoning about the meta theory. So you'll see that the translation on terms in the Lambda Act to Lambda CH translation here. Here we have this extra CH parameter to this. This is completely irrelevant in the value case. So it gets a bit messier if you don't do the separation. I mean, it's perfectly possible to do the translation. There's no inherent problem with doing so. It just simplifies reasoning about the meta theory.
Okay, because there's no notion of beta equivalence or substitution anymore when you have that in your calculus. So, I mean, I think it's more like you should, I think you should have those basic notions from the Lambda calculus in the, if you do substitution for a variable, then you can't type send anymore. Okay.
So that's not true. You still have a notion of substitution in fine-grained call by value. It's completely standard. I mean, you can substitute a value for a variable. It's a little bit more involved, but you do still have a substitution theorem.
This is my first time seeing
it. Okay. It's just like, it's like a normal form or CPS.
So maybe this is something you're investigating, but it was a little bit surprising that you typed actors with a type that assumes the same kind of message coming in every time, because typically an actor is able to transform itself, and usually, at least in many cases, that's because it's going to receive a different kind of message next. So maybe the question is, do you think that session types will actually help deal with this problem of type, I forgot what you called it, merging?
That is a brilliant question. So I do have a version of this calculus where we naively add some form of behavioral typing to the language. Essentially what this means is instead of having a single type of mailbox, you essentially end up having a vector of types. So instead of saying, right, I'm going to receive integers or strings, it says I will receive an integer, then a string, and a Boolean. Now the issue with this is in order to have type soundness, at least as far as we've investigated, we need linear types. So we've had a look at the translations in this particular setting, and we find that that particular formulation isn't as expressive. We can't really do a whole lot with it. But there is ongoing work, I think, there is ongoing work investigating variants of this question. But yes, we have had a little look at it, and negative results so far on that front.
In particular, the actor paradigm has been developed originally without types. So perhaps it would be interesting to see what are the translations when we have no types, and then we go to types.
That is a great question. So I think the reason why I personally started with type calculi is because I wanted to actually have a look at the theory behind type parameterized actors. So type parameterized actors have been fairly recently proposed, and actually having a typed formalism was quite important when I started this work. I would conjecture actually that the translations probably wouldn't be all that different, except the restriction of having to flatten out all the channel types beforehand. Where is it? This one wouldn't need to be done. So I think that's probably the main difference there. But thank you for the question.
The other question would be, why don't you attach to each actor as many channels as kind of things that they have?
So, is your question, I'm restricting this to a single mailbox as opposed to multiple mailboxes?
You would give to an actor as many different mailboxes as there are kind of messages they can receive, and then you don't need to do this coalescing.
Yeah, so that's an interesting point. Then what happens is you do lose the temporal ordering that you get with a standard mailbox. That would end up being a bit like Cloud Haskell, for example, and using some form of input guarded choice. But yes, that would definitely solve the coalescing, remove the need for coalescing. Thanks very much.